8 years back. Same July month, we started the first lecture with Dr. Murugan is here as a Stephen Atkins Memorial Lecture. It was PSL 1 in 2018. So 7 years has crossed. So we are at 92nd lecture. Soon we will going to complete the 100th lecture. So we are going to have a lecture from Dr. Balakrishnan. So before we start the lecture, let me make a brief introduction about the Tamil Nadu Science Forum. TNSF is a voluntary science organization. It's meant for popularizing the science. It started by few research scholars in Chennai University in 1980s. Dr. Murugan, Dr. TRG, Dr. T. Jayaraman, all of them were doing their Ph.D. in theoretical physics department, and they joined together and formed the Science Forum. And initially it was holding some meetings, hall meetings. Their idea is to go beyond physics and learn something out of physics. And they want to get knowledge about all disciplines. So it was a lecture meant for only students. Later, they thought that the science popularization can be taken to the ordinary common man who is not in science, but they are using science on day-to-day basis. So they go to the different places and organize some lectures in the streets, and they have slides and doing slideshow lectures in the streets. So thereby it becomes it's coming out of the campus and go to the people. So it became a real people science movement. In 1986, while doing this, there was a demand from other district hospitals. They started a science jata from Kanyakumari, and it reaches Chennai. And during the journey of 750 kilometers, it went through different villages and had a lot of lectures on science. And in 1987, we started a magazine called Tulir. It's meant for students, children's science magazine in Tamil. And 91, we started a magazine in Jantar Mantar. In 90s, now the Science Forum is getting involved in the literacy movement, functional literacy movement. And we get into we were appointed as a nodal agency for implementing the government literacy scheme of functional literacy. We get into the Virudhunagar district. We make the 100% literate district. And then we get into the Pudukkottai. Then the whole scheme was expanded to entire Tamil Nadu. Today, Tamil Nadu has reached a level where more than 90% of the people are able to read and write. So this was the basic work done by TNSF in 90s. So while doing this, we get a lot of volunteers, and the organization has grown, and it become truly a Tamil Nadu organization. So now it is working under 7 different areas. One is its bread and butter is popularizing the science popularization. And the second one is the science publications. So we already started publishing a couple of magazines in the Stolir and the Jantar Mantar. And we also launched 3 more magazines, Virudhu, Vijnana Chiragu, some more magazines. And we also start publishing books in Tamil, science books in Tamil. So we have a separate publication group. And the third one is we want to bring more women in science. We name as Samam. Samam is meant for bringing women in STEM. And the fourth one is we are working in the health and education. And we are also working in education as well, environment and development. Finally, the 7th one is the youth for science. So these are all the 7 areas we are working in. And I always request you to become a member of Science Forum. It's very simple. It's the subscription is 50 only. We have the QR code. Just scan the QR code, fill up the form, and submit. You can also make the subscription through GPay. That's it. It's easy. And you can be part of any of the 7 activities which you are interested in. If you are interested in working on environment, you become a part of environment group. If you are interested in working on the education, you can be a part of education group. If you are working on the summum, you can be if you want to focus more on the science writing, you become a science publication group. There are a lot of opportunities to unleash your talent in Tamil Nadu Science Forum. With this, let us start this lecture. I want to introduce the speaker. Dr. Balakrishnan in the academic circles. He was a popular communicator, and you see that the crowd which has come here, that research indicates very he's a theoretical physicist. He has worked in a number of fields and areas, including the particle physics, many body theory, the mechanical behavior of solids, dynamical system, stochastic process, and quantum dynamics. He is an accomplished researcher who has made important contribution to the theory of elasticity, continuous scheme, time random walk, and recurrence in dynamic system. He received his PhD from Brandeis University. He was with the IIT. He was elected as a fellow of Indian Academy of Sciences in 1985. He has a couple of hours. So he is going to talk about scaling in the natural sciences and beyond.
Dr. Vijayan, my mic is not. Thank you, Dr. Vijayan, for the kind introduction, and good morning to all of you. I thank the Science Forum, the Tamil Nadu Science Forum, for giving me this opportunity to talk to you. And I have to apologize for several things. First of all, my voice is going, so I'm not sure if I'm going to reach the back. I hope the mic works properly. The second thing is, this talk is a little old because a couple of years ago, I was to lecture here in the same forum in December 2023. And then for one reason or the other, it got postponed, and I prepared the talk in a hurry at that time to meet the deadline, and then I never got back to it. So it's something which I wrote by hand and then scanned, so it may not be perfect as presentations go these days. I'm not even sure if it's legible from the back. Is it legible? Can you see at all? I'll try to read whatever is written there, but I hope it's not too works out reasonably well. The title is a little more extended than I'd given earlier, which is Scaling in Natural Sciences and Beyond. I've added scaling behavior, scale invariance, and power laws here because that's going to be the theme of what I want to say. A little couple of words on why I wrote this talk out at all, why I chose this as a topic, was that I was extremely discontented over the years, at various stages in my career, with the textbooks that were written on various subjects. In particular, I was extremely discontented with the way science was taught, not only at the undergraduate level, but postgraduate level as well. And the trouble starts at the school stage for reasons which cannot really be avoided, but certainly can be avoided at the college stage. And that's the following. You take a subject like physics, it's a vast subject. It's got a wide pasture. It's 400 years old in its modern form. So a lot of problems have been investigated by a lot of very clever people who are added to the body of science. But a student who undergoes the standard curriculum has no concept that the subject has underlying unifying themes at all. That's never mentioned. At a trite level, let me give an example. Students learn in high school in the 11th standard or something like that about the ideal gas. They learn of Charles's law, Henry's law, Boyle's law, everybody else's law, etc. We're rarely told that there's just one equation of state, PV equal to nRT for the ideal gas, and that from all other laws follow from that equation of state. This is a simple thing which is not pointed out, and I've always wondered why. So I started asking myself whether there's an underlying structure with which one can introduce physics. So if you like, this talk is going to be an introduction to physics itself, into science and a way of thinking itself. So I'm going to give a large number of examples from various subjects, as many as I could think of. And I'm sure we realize immediately that I'm not an expert in most of those subjects, but then the gem of the idea is there. The germ of the idea is there, and you should be able to connect up the dots in between. So with that, let me get to this talk itself. Let's go. Why is this happening? Yeah. The first point I want to make is the enormous range of physical parameters in this universe. And that's, I think, the first thing that should be taught to physics students is when they reach the 11th standard or something like that. The enormous range, simply the mind-boggling range of physical parameters, all the parameters that you can think of. So we'll do a little thought experiment. The first item is the following. We try to deduce the laws of physics. We try to deduce what the universe looks like using our bare senses. So no instruments, no analysis, no mathematics, no logical reasoning or anything like that, just observation. That's the first way of doing it. The second way, we bring into bear all our mathematical tools, all the analysis we developed, all the instruments we developed, every one of them, including the largest microscope you can think of, which is the Large Hadron Collider, etc. The most powerful telescopes, everything is allowed. And then what range do we uncover? And then you're in for a little surprise. If you do it by part A and part B, you get two different answers altogether. In part A, which where we use our bare senses, you're not allowed to use any help at all. In part B, you use all the help that we can get from modern science. Okay. And let's focus on three parameters, the mass, length, and time, but just for convenience, because they form fundamental units. So what's the smallest mass that one can think of, that one can lift? And what's the largest you can lift? The smallest mass that we can distinguish between is probably a gram or something like that. Just we are not doing orders of magnitude, so it's not going to be exact. About a gram, we can tell the difference between 1 gram and 10 grams with our bare senses by hefting the object. We can tell the difference between a leaf and a rock by hefting the object. But we certainly cannot tell the difference between a milligram and a microgram, or a microgram and a picogram at all. At the other end of the scale, the largest mass that you can think of is something that you can control. You know the difference between 1 kilogram and 10 kilograms, or between 10 kilograms and 100 kilograms. But beyond about 100 kilograms, there's no way in which bare senses will tell us what the actual weight of the object is if I don't tell you its density. There's this big lump of metal sitting there, and you can't push it. You can't push it, you sort of realize it's more than 100 kilos, definitely for sure. But whether it's 1,000 kilos or 10,000 kilos, we have no way of saying at all. So again, you're restricted on the other end by about 10 to 3 grams or some kilograms or something like that. What about length? Well, the smallest length we can think of is a fine human hair. We can resolve it with our eyes. That's about a fraction of a millimeter, tenth of a millimeter. So 10 to the minus 4 meters is the smallest length we can resolve. And what's the largest length we can resolve? You look at this night sky, you look at the stars and the planets, you have no clue as to which is near and which is far. You have no idea what the distance is like at all. The only way you can do it is look around straight with your eyes, and at best you can see about 10 kilometers at best. Certainly not 100 kilometers or 1,000 kilometers. 10 kilometers on a clear day. In Chennai, you can probably see 100 meters on Mount Road, or even less. In Delhi, you can't see at all, but then certainly. So once again, it's a range from 10 to the minus 4 meters to about 10 kilometers, range of 7 or 8 orders of magnitude, etc. What about time? The smallest time that we can resolve with our bare senses is perhaps you would guess our pulse or something like that, a second, 72-second pulses per second. So maybe a second is the smallest time you can distinguish between. But actually, biologically, there's a faster time scale, which is the blink of an eye, which is a tenth of a second. So 10 to the minus 1 second. And what's the largest length scale you can, time scale that you can reduce with our bare senses? Well, people have done this experiment. They've put subjects in chambers without signals from outside. There's a kind of uniform lighting, so you can't tell whether it's morning, evening, afternoon, or night. You can't do anything of that kind. Periodically, a hole opens in the wall, and the food is pushed in, and the food is taken from one of our hostels, so you can't tell if it's breakfast, lunch, or dinner. So no time indicators of this kind at all. And how long can you then say? Well, the experimental subjects have been told to press a button in this wall every time they think an hour has elapsed. And this experiment has been done several times. And what happens soon, within about a day or so, is that the subject starts pressing the button faster and slower. So time moves actually more slowly for these people. It sometimes stretches as much as 2 or 3 hours before they think an hour is elapsed. This experiment was done and was reported in Resonance many years ago. The lady who was the subject of the experiment lasted 2 months or some such thing. I forget the exact period before she realized, before the experiment was cut short, because what happened was Rajiv Gandhi got assassinated and the experimental subject was pulled out because it would have been too much of a shock otherwise. The experiment was aborted in between, but about a couple of months or so. So 2 months, I would say, is about what you can distinguish with the bare senses. After that, time appears to drag on. Okay. So again, look at the orders of magnitude involved. So both mass and mass length versus as well as time, these are the upper and lower bounds on what we can distinguish with our bare senses. But look at what nature is doing. The smallest mass we can think of is we can measure it is the electron's mass, 10 to the minus 30 kilograms. And what's the largest mass we measured? Well, it's the mass of the universe. And the mass of the universe is the number of stars, 10 to the 22 stars or so in the known universe, multiplied by the number of the dust in between, the hydrogen cloud, etc., the dark matter, which is more 90% dark matter and dark energy, which is 95% of the universe. You do all that and you get a range at least 10 to the 60 kilograms, at least. So look at the number of orders of magnitude. 90 orders of magnitude here is what we're dealing with when we deal with mass and nature. What about length? You can construct a length out of the three real fundamental constants of nature. Now, again, I think students should be told at an early stage that when I ask young students what a constant of nature is or something, fundamental constant, they name the gas constant and so on. Understandable. This is extremely understandable. Sometimes someone should tell them that the constants of nature has provided us with three constants, fundamental constants. If you're a string theorist, there's only one fundamental constant. But let's skip that for a moment. First constant of motion is capital G, Newton's gravitational constant, which determines the large-scale nature of the universe. So the largest scales, the universe is governed by capital G. Second constant of motion is the speed of light in vacuum, little c, which is there because the universe is relativistic. It's telling us the universe is relativistic. The third constant of motion nature has provided us with is a quantum of action, which is Planck's constant H, which tells us that the universe is quantum mechanical. So these are the three fundamental constants that reduce it. In fact, if people in particle physics are familiar with the fact that it's so-called natural units, you put H equal to 1, C equal to 1, and so on, and then you have only one fundamental constant of nature, capital G, which the string theorists like to call the string tension, related to it in some case. We won't get there, but G, H, and C are the three fundamental constants. And they have physical dimensions in terms of M, L, and T. One can ask then, can you construct a mass, length, and time using these three constants? And yes, you can. The time constant that you can use is first one is the length constant, which you can use, which I've written here as h cross c over g cubed. That's wrong. It's h cross g divided by c cubed. It should be the other way. G and c should be interchanged. And this is of the order of 10 to the minus 35 meters. 10 to the minus 35 meters is 20 orders of magnitude smaller than anything we've penetrated. The shortest distances we can think of are strong interaction distances, etc., which is of the order of 10 to the minus 15, 18 or so at best in meters. But this is for 17 orders of magnitude smaller than that. Smaller than that, the length idea of a continuous length as a continuous variable breaks down and quantum fluctuations take over. So space-time fluctuates like a froth, quantum froth. And therefore, the concept of a continuous length going to zero is not there. The Planck's constant is the smallest length scale you can think of. Similarly, once you have a length scale, you divide by c, you get a time scale, that's a Planck time, and that's 10 to the minus 43 seconds. That is why you get these popular books tell you that we don't know what happened in the first 10 to the minus 43 seconds after the Big Bang, but we know what's pretty much a good idea of what's happened after that. Now, this is a little bit of a stretch of the imagination. We really don't know what happened after that. And we really don't know what happened at the time of the Big Bang, etc. In fact, even that is a fallacy because the Big Bang is still going on. It's not exponentially expanding, but it's still going on in that sense. So whatever it is, we have a length scale and we have a time scale. What about a mass scale? Can you construct a mass scale? 10 to the minus 30 is the lowest mass of the particles that we can think of, like the electron. The photon is believed to have a zero mass. Of course, now in physics, there's no such thing as saying something is exactly equal to zero. What you have to do is to put an upper bound on it. And what we know is that the photon mass is at least 10 to the minus, not bigger than 10 to the minus 60 kilos or so. That's all one can say. One can't say it's exactly equal to zero. Because if we took it to be non-zero, you have a lot of other consequences, but now people are still measuring the boundaries to find out what the best bound that you can put on this stuff is. But that's another story altogether. Whatever it is, nature has a time scale called the Planck time. What about Planck mass? If you calculate Planck mass, turns out to be square root of CH cross over G, you compute it in standard international units, you end up with 10 to the minus 8 kilos. That's macroscopic, that's huge. Because 10 to the 8 kilos in daily life is not much, but it's a huge mass in that sense, in particle physics terms. What happened there? For the length, you got the smallest length scale you can conceive of. For time, you got the smallest time scale you can conceive of. For mass, you're getting an enormous scale. What happens is interesting. This is the largest mass an elementary particle can have, not the smallest. Because you put in as much energy as is there in a Planck mass, in a volume which is Planck mass cube, it becomes a black hole and disappears forever. So you can't go beyond that. That also should tell you that accelerator physics has a physical limit. People talk about accelerators becoming as big as a galaxy. You have a circle which is as big as a galaxy and so on. But it's a mug's game because sooner or later it's going to end up in a black hole. Okay, so that's just an aside. Whatever it is, nature has a time scale, mass scale, and length scale. And now look at what happens when you compare these two. Yeah. So in mass, nature runs from 10 to the minus whatever it is, 10 to the minus 30 to over 10 to the 55 or so, 10 to the 10, that's 55 is an underestimate. It should be at least 10 to the 60 on that side. Similarly, in length, it goes all the way from 10 to the minus 35 meters to the edge of the universe, which is 10 to the 26 meters away, approximately, to the known universe. And similarly, in time, it runs all the way from 10 to the minus 42, so 43 seconds, to 10 to the 17, which is the age of the universe at the present time, 13.7 billion years. Okay. And what we are sitting in is in the middle world of what I call middle dimension, this narrow range of 7 or 8 orders of magnitude, which is all our direct senses can perceive. But outside it lies a vast universe. Now, once you're given this, will any rational person say that what happens in this middle range that we are familiar with is going to govern the rest of the range? It's obviously not true at all. Now, the world of middle dimensions we've come to terms with. We've got a facility to handle. We know, for instance, that it's important for us, for evolutionary reasons, to understand that a rock is better thrown at a tiger than at a leaf. Human beings know that intuitively. So my point is that our brains are hardwired. What we call facility with what we call normal Newtonian physics is the kind of facility which the brain has been hardwired to for the sake of survival, not for the sake of understanding string theory. That's a bonus for which we ought to give thanks to whatever is the power is controlling the whole thing, if any. So when students say that relativity is counterintuitive, quantum mechanics is counterintuitive, and so on, I put it to you that Newtonian mechanics is counterintuitive. It took us 3,000 years to discover that if you apply a force to an object, you change its momentum and not its position, which may change as a consequence of the momentum changing, not directly. The only objects that for which the force is proportional to the velocity will be bacteria floating in a neutron solution at terminal velocity. For them, the force is proportional to the velocity, not the acceleration. But everywhere else, its force is proportional to the acceleration. So Newton's law is just as counterintuitive as quantum mechanics is in some sense, except that we're more familiar with it, we have more facility with it, but facility shouldn't be confused with understanding. And that's the point that should be driven home early in education, I think. So what do we do to deal with this huge range of physical parameters? Well, we look for general principles. We look for underlying principles like symmetry and invariance and conservation principles, etc., dimensional analysis, scaling. Something scales like the square of something, etc., etc. And that's going to be the theme of what I'm going to say next in various examples. Here's a simple example of power law for students who are in 9th standard or 10th standard. When they really say PV equal to constant, it's better to say P is proportional to the inverse of the velocity, reciprocal of the velocity. So that -1 is an exponent, and the whole of modern physics has to do with exponents. You find exponents, critical exponents, etc., etc. So that's the basic lesson. You change the process to an adiabatic process, and you get P proportional to V to the minus gamma. So that's an exponent here. And this is rife, the whole of nature is rife with these power laws. For instance, Pareto's law of income distribution, wealth distribution. It's well known that 80% of the wealth in the world is held in the hands of 20% of the population. But the model here is that no matter how rich you are, there's somebody richer. No matter how poor you are, there's somebody poorer. There's no scale here at all. So that was one of the early observations. And this is in an artificial subject like economics, not necessarily a scientific subject in that sense, the traditional sense. Natural disasters seem to obey power laws, and the most common one that's known to us is the Gutenberg-Richter law for earthquakes, where the frequency of earthquakes of a certain magnitude is proportional to constant divided by 10 to the power magnitude, 10 or any exponent to the power, any number raised to a positive number raised to this power n. That's the Gutenberg-Richter law. Zipf's law in linguistics, that too has a power law. You look at the frequency of words appearing in any language in the literature, then on the average, statistically, there's a power law here. So the frequency with which a word appears is 1 over the rank of this word in the frequency table. Once again, with an exponent very close to 1. And that works even for letters, individual letters in a language. For instance, it's well known that in English, ETAOINSHRDLU is it appears in one of Sherlock Holmes stories, is the frequency order in which individual letters appear. We're talking about on the average, not these artificial preparations where you write a whole sentence without the word E, without the letter E, and so on. Those are exceptions. And so on. So here's an example, again taken from high school, on the usefulness of dimensional analysis. By the way, one simple question from earlier, what I said earlier. Capital G, H, and C are the two fundamental constants of nature. And we found from that the quantity of dimensions mass, the Planck length, and the Planck time. Uniquely, these are unique solutions. The question that should be asked in class is, can I find a dimensionless constant from H, G, and L, and C? Can I find a dimensional constant from there? It should be obvious that because you can find a length scale, a mass scale, and a time scale uniquely, you cannot find a dimensionless number. So if you had a dimensionless combination of that kind, that would be a very special number. It would be independent of units. So there is no such number in the universe, except perhaps 1. You need 0 and you need a 1 for everything, right? So there's no special number in the universe, not even 42, apologies to Douglas Adams. So one asks the question, what's the time period of a simple pendulum undergoing simple oscillations, harmonic oscillations? And of course, the answer is square root of L over G, which comes by people saying that it can at best depend on the mass of the bob, on the length of the pendulum, and on little g, gravity. Yeah. With that, you do a simple counting of powers of ml and t, and you discover square root of L over G. You don't get 2 pi factor, that's purely numerical. It has to be determined by analysis. But you get square root of L over G. I object to this example giving the big scope for the following reason. Why shouldn't it also depend on the speed of light in a vacuum? It's a fundamental constant. Why shouldn't it depend on gravitational constant? Why shouldn't it depend on Planck's constant? What about Boltzmann's constant, etc.? And I think the answer should be given for each of these points. It doesn't depend on Planck's constant because it's not a quantum mechanical object, classical mechanics. It doesn't depend on the speed of light because the bob is not charged. There's no electricity, there's no magnetism, there's no relativity, it's not relativity. It doesn't depend on capital G because it does depend on capital G. It's encompassed in little g, which is gm or r squared, etc. Certainly depend on capital G. The moment you put that in, then you have 3 equations and 3 unknowns for 3 powers, and you can solve this problem. But the way it's written is this problem is solved and memorized, beautifully memorized by generations of students, which doesn't make sense. But then this question should be asked, why doesn't it depend on other things? So let me give an example of what happens if it does depend on other things. Can you move this? Yeah, this is the famous reduction of the power of the first nuclear explosion in Los Alamos in July 1945. They did the Trinity test, and there was a yield of about 20 kilotons or so. Subsequently, a newspaper published a photograph of the explosion showing the fireball, which was about 140 meters in radius, taken 25 milliseconds after the explosion. And based on that, G.I. Taylor, one of the great hydrodynamicists of our time, the British hydrodynamicist, reduced the yield of the explosion because he said, argued that a certain volume of air had to be displaced by this blast wave. And given the size of the blast wave, he said the energy, the radius of this blast wave must be dependent on the blast energy E, the time of the fireball was photographed with little t, and the density of air, because that's what it takes to move that much air. And by dimensional analysis, he found that if you solve for E, you end up with a simple formula in terms of the radius, the time, and the density of air. And this calculation gave him something like 10 to the power 14 joules. And if you realize that 4 terajoules is equal to 1000 kilotons, 100 kilotons of 1000 kilotons of TNT, then the blast energy comes out to be about 20 or so. So it's pretty close to the correct answer of 19. This is proof, I give this as proof that secrets cannot be, scientific secrets don't exist. If you're clever enough, you can deduce from the data given, you can deduce pretty much everything. That's a useful thing in dimensional analysis, a useful example. What is interesting about it is that exactly the same argument was given for handling supernova in 1987, the supernova of 1987, in which from the size of the nebula, you could also deduce what the power of the explosion was. Calculating backwards what the time taken was for the photograph. So again, an exotic example. Here's a mundane example. When you look at flow, quasi-flow in a fluid, of a fluid, non-turbulent laminar flow of a fluid through a circular cross-section pipe, we know that the rate of discharge, the volume per unit tank, will be proportional to the cross-sectional area of this pipe multiplied by the velocity of the flow. When you do that, you get pi r squared times v, and that should be the proportionality constant for the velocity, some constant times that, etc. And then you discover that when these people are laying pipes for flats and so on, they do it at midnight, late at night. And I've always been very skeptical about it because the argument is that they don't want to block traffic and so on. This might be ostensibly true, but I have never seen any civic authorities really worry about blocking traffic. It certainly is not one of their concerns at all. So you go a little deeper and you discover that actually you've got to be a little careful. The dependence of the discharge rate is not the square of the radius, but the fourth power of the radius. We're very careful about this. And therefore, if somebody exchanges a 1-inch pipe for a half-inch pipe, which is sanctioned, they get 16 times the water. It makes everybody nap, including the real estate agents. They charge you extra. And why does that happen? The answer is it's because the velocity is not uniform across the pipe cross-section. It's fastest at the center and the axis of the pipe and slowest at the edges. And at the edges, because of the viscosity of water, the velocity is technically zero actually. And the velocity profile is with this parabolic shape that I'm showing here at the bottom. Here. Now we ask, so what can the average velocity depend on? We need an average. Well, it can depend on the pressure head, the inlet pressure minus the outlet pressure divided by the length of the horizontal pipe. That's delta P over L. It should also depend on the viscosity, of course. It should also depend on the radius itself, on the radius of the pipe. And you do a little bit of dimensional analysis, and lo and behold, you discover that V average is proportional to R squared, and multiplying by the other pi R squared from the area cross section, you get R4 once again, with the viscosity present here. There's a subtlety involved here. The moment you have two parameters of the same dimensions in a physical problem, you can't do dimensional analysis because the answer could always be multiplied by a function of the ratio of these two parameters, which is dimensionless. That doesn't happen here because we very cleverly said that the horizontal length of the pipe doesn't matter. What matters is the pressure head, which is P1 minus P2 or P inlet minus P outlet divided by the length of the pipe. So the length gets subsumed in this delta P over L, and you're back to this flow, normal law flow, Poisson flow. So once again, it's an example that should be pointed out when teaching this subject. And now we come to Kepler's third law. Here's another way in which dynamical scaling analysis actually gives you a dynamical relation, which is Kepler's third law, which says that the square of the time period is proportional to the cube of the average radius for an elliptical orbit or something like that. Okay, so we write down Newton's equation, which is md2r over dt2 is the force, which is the central force here. And then you say, look, this law I'm not happy with the units you choose. You choose meters, I like to choose feet because I like the King of England. And you choose seconds, I'd like to choose minutes, just for the heck of it, and so on. And the law should be exactly the same in both cases. So you change R to R prime, which is lambda times R or something like that. And you change T to T prime, which is mu times T, for instance. And then you write Newton's third law, or Kepler's law, Newton's law for the planetary motion once again. And you discover that if you change the time scale and length scale by lambda and mu relatively, for getting the same invariant object, the final orbit should be independent of the units you choose. You discover that mu squared is proportional to lambda to the n plus 1. So we've done this for a law which is not just 1 over r squared, but a force law which is 1 over r to the power n, where n can be any integer, any positive number. So if mu squared is proportional to t to the mu squared is proportional to lambda to the n plus 1, if you put n equal to minus 1, minus 2, n equal to 2 in the denominator here, 1 over r to the n, you end up with Kepler's third law. So what it's saying, you've got to be very careful about what it's saying. It is not saying that the planets move in ellipses with Kepler's third law valid or anything like that. It's saying that the 1 over r squared force, the inverse square law of force in 3 dimensions, 3 physical dimensions, is such that if the system supports, if the initial conditions support a closed orbit, an elliptical orbit of mean size r1 with time period t1, it will also support an orbit with radius r2 with time period t2 such that r1 squared over r2 squared, r1 cubed over r2 cubed is t1 squared over t2 squared. That's all it says. And that's the point. That law, the way you derived it, doesn't even assume elliptical orbits. It's true even for hyperbolic orbits with proper interpretation of r and t. So again, it's dynamical information which is coming straight from this. As a bonus, if you put n equal to minus 1 in this law, then you get a force which is proportional to r, the rate of displacement itself, which is of course the familiar simple harmonic oscillator. And n plus 1 becomes 0 in that case, and then the time period is independent of the length scale, which takes us back to our original statement that in simple harmonic motion, the time period is independent of the amplitude, a fact which Galileo discovered. So the so-called isochronicity of the pendulum, the simple pendulum and small oscillations, is a byproduct of this argument here, the general argument. So again, I'm trying to show how simple arguments can be generalized and how they lead to valuable information. One needs to give students enough time to think about what they're learning, because I'm afraid our curricula are so packed with material that that doesn't happen at all. But they have to be able to have some time to think and make all the mistakes that can be made, and then see what's the maximum you can extract from any given information. Similarly, Coulomb's law, it follows from the fact, Gauss's law follows from the fact that, you find the electric flux around over a closed surface and you know what the charges inside it are. It's like walking around the compound of a building and telling you everything that's inside the house here. And this is magic is possible because, as we know, the inverse square law drops like 1 over r squared, and the surface area increases like r squared in 3 dimensions, and these two cancel each other out. And that's not going to be true in any other dimensionality with the 1 over r squared force law. It should be 1 over r to the d minus 2 and so on. So once again, d minus 1. So once again, this tells you that these laws arise because of general scaling relations, not because of a particular force that's used or anything like that. Here's an example from biology, which is kind of amusing. And this is also essential because now people think that these subjects are all different from each other and none of them is extendable to anything else. Well, we do this experiment in biology, this fact in biology, that if you take mammals across a huge range of mammals, from mice to all the way to horses and giraffes and so on, you ask what's the height to which an animal can jump from a standing position, not taking a running jump, but a standing position. This height, peculiarly, is just a few centimeters, or certainly about a meter or so at best for most animals, maybe 2 meters if you're an Olympic high jumper or something. I'm leaving out animals which are specially constructed for the purpose of jumping, like fleas and frogs. These animals are constructed in such a way, the skeletal framework is constructed in such a way that they aid in jumping. But I'm talking about generic mammals, for instance. Then you discover that the height is pretty much independent of the size of the animal at all. Can you understand this at all? And the answer is yes. You can understand it by the following very crude, rough argument, but it's valid, actually, can be straightened out. First, we assume that the animals are all spheres. That's the first thing a physicist does, to assume the simplest model. Linear, linear length, linear dimension L, something. And then to jump a height h, the work that has to be done is mgh, working against gravity, right? Now m is proportional to the volume of the animal times the density of the material. And most of the animals are made of water, mostly, so it's common to think. And therefore, it's proportional to L cubed h. That's the work done. And what's the power that you can generate? The power depends on your muscular structure, and the muscles are tethered to the skeleton, so that's dependent on the skeletal framework dimension, which is proportional to the cross-sectional area of the animal, so L squared. So on the left-hand side, you have the work done divided by power is L cubed h over L. On the right-hand side, you want to know how much animal power can the animal, how much energy does the animal store? It stores in finely ATP molecules in the mitochondria and so on, but it's finely proportional to the volume of the animal. So that's an L cube. And then unless the animal has a way of dissipating the heat that occurs during the work being done, the animal will die heat death. Therefore, it needs to evaporate perspiration, for instance, which will depend on the surface area of the animal, which is L squared. So you have L cubed h over L squared is L cubed over L squared, which says h is independent of L altogether. So that tells you why these animals can jump approximately the same height in order of magnitude, no matter what the size of the animal is. So it's a valid argument, completely valid argument. Okay, very simplistic. You can, of course, find exceptions and so on. But I'm trying to point out the universality of these arguments here. And this one illustrates the fact that you can't do the work without generating heat. And you need to dissipate the heat, otherwise the animal dies a heat death. What about going on land? How far can an animal go if you want to take a long route? Once again, I won't go through this argument. A similar thing tells you that these animals all walk at constant speed and so on. Then the time for which the animal can continue depends on the linear dimension of that animal, and it's proportional to t, the L itself. So it ends up with a statement that if you want to go on a long hike, a long safari, take an elephant, don't take a mule. On the other hand, if you want to climb up a hill, then a similar argument shows that you should take the animal with a muscular strength that's minimal to what is needed. So you don't take an elephant, you take a mule. Not even a horse, but a mule. Because that can go further up a hill without gasping. So a cat, as you all know, runs up a hill without gasping, but an elephant would gasp before it does that. By the way, there's an analogy in history, there's a lesson in history there. We're told that Hannibal in Europe in ancient Europe brought elephants down the Alps and vanquished his enemies. I'm sure he did that because no enemy was expecting elephants to come down a hill. They would have thought, no, that is a militarily very not satisfactory solution to the problem. So the element of surprise was on Hannibal's side. So history really helped. It really helped. Yeah. Similarly, there are other interesting laws in physiology and medicine which are not fully explained. For instance, the heartbeat rate and the longevity of an animal go like n to the power 1/4 and n to the power minus 1/4 respectively. And that's across 6 orders of magnitudes for mammals. What is it telling us finally? It's saying the number of heartbeats multiplied by the number of years that your total longevity multiplied by the heartbeat rate is going to give you the total number of heartbeats. And it's telling you that roughly the total number of heartbeats for all these animals across 6 orders of magnitude is exactly the same. It's just that the mouse finishes off its heartbeats faster, at a faster rate and dies, whereas an elephant takes much longer. Eventually, this is not surprising because the muscular structure is exactly the same in all these animals. The muscles are made of pretty much the same elements in the same way, for mammals at least. There are other laws like the Kleiber's law for the heart, metabolic rate, etc., for which there are theories in statistical mechanics. And I've got a couple of slides here to show that, but it gets technical, so I won't do that. Let me go on to scaling in thermodynamics. We taught the first 2 laws of thermodynamics, but there's very important law that's left out. We write the laws of thermodynamics in the form dq is TdS, and TdS is du plus PdV minus mu dN, where mu is the chemical potential. But what is important is not just that, there's also a property called extensivity, which says that the internal energy, for instance, is a homogeneous function of S, V, and N, the entropy, the volume, and the number of particles, a homogeneous function of degree 1. which means Euler's theorem in calculus immediately tells you there's a relation for the partial derivatives of u, the internal energy with these variables. And if you do that, you get immediately a handle on what Gibbs' law is. It gives you a handle on what the chemical potential is, which is basically the Gibbs free energy per particle. It also tells you the Gibbs-Duhem law, which says the chemical potential is a function of pressure and temperature alone. Follows exactly immediately from extensivity. If you don't have extensivity, you're in trouble. Thermodynamically unstable situations start happening. So you need to put that constraint in right in the beginning. Even the very stability of matter itself, which is a non-trivial problem solved in the last century by Dyson and Lee and Leonard and other people, a whole host of people, is actually non-trivial. It has to do with very subtle effects. It turns out that matter is stable with both positive and negative charges inside. You have positive atoms and you have nuclei and you have negative electrons. You take a piece of metal, for instance. Why is it in stable equilibrium, thermal equilibrium? Because these guys could be attracting each other, collapsing, and so on. So if you start with k nuclei and n electrons, you soon discover that the energy is proportional to k times n, and repulsive energy is proportional to n squared. So if you double the size of the object, the internal energy increases by a factor of 4, which is not tenable, sustainable by stable thermodynamical arguments. So what happens here? And then it's a non-trivial problem solved by people very carefully over the years. A whole bunch of people is involved with this thing, starting with Dyson and so on. It turns out, to cut a long story short, it turns out that the energy is indeed extensive. It is indeed proportional to the first power of k and n, number of nuclei and the number of electrons. But what happens in between is subtle quantum mechanics, and quantum mechanics is what keeps matter stable. So when one is asked what is the use of quantum mechanics, normally one says the particle in a box, hydrogen atom and stuff like that. Uses is all of nature. Matter is impenetrable not because of Coulomb repulsion, but because of the Pauli exclusion principle. That's the reason I'm not able to put a solid through another solid. And that's what keeps matter stable on top of it. So it's very subtle cancellations occur, and the final end result is that matter is stable indeed in its form. So again, another point worth pointing out here. The whole of phase transitions, the whole of critical phenomena is based on the fact of scaling or scaling properties and critical exponents and so on. I'm not going to get into the details of this, but the most interesting part of this PT diagram is the point where the liquid gas coexistence line ends in a critical point abruptly. At that point, thermodynamics fades and fluctuations become as large as the mean itself. And the central limit theorem fades, or probability theory fades, and you have a phase transition, a continuous phase transition. And then interesting question is what are the scaling exponents here at this critical point? And that's what got the Nobel Prize for the last century when the problem of equilibrium statistical mechanics, phase transitions in equilibrium statistical mechanics was solved using the normalization group. And there was a whole new technique which has been used subsequently in many, many areas because it takes into account the fact that unlike normal thermodynamic phases, where the mean value of any thermodynamic observable is very large compared to the scatter in that mean value, scatter about the mean value. In fact, the relative fluctuation of the standard deviation divided by mean is typically proportional to 1 over square root of the number of degrees of freedom, and which is Avogadro's number of 10 times that. Therefore, thermodynamics is fine till you hit a critical point, and then thermodynamics fails because you have fluctuations on all length scales, all time scales, and you need to take a technique called the renormalization group to deal with this situation. Okay. And that's been done at least in equilibrium critical phenomena. So once again, very simple considerations, but very profound consequences. In fact, I think statistical mechanics, this part of it should be taught by starting with critical phenomena and explain the role of fluctuations in it. Yeah. Typically, in the normal circumstance, thermodynamics is grouped to 1 part in 10 to the 12 because typically you have 10 times Avogadro's number in a sample, and then the fluctuations, relative fluctuations are proportional to 1 over square root of 10 to the 24, which is 1 part in 10 to the 12. Well, I'm not going to get into the details of critical phenomena here, and we'll leave out. Dynamics is a subject rife with power laws, scaling laws, and so on. It was recognized in the old days, starting with Kolmogorov. And you have this little ditty by Richardson, big worlds of little worlds and so on, etc., finally to viscosity, saying that finally big eddies have smaller eddies, they transfer their energy. There's a cascade of energy transfer from larger eddies to smaller eddies. Finally, the eddies get so small that viscous damping takes over and there's dissipation completely. So that's the model of the story here. It also answers questions like what is the smallest size of a cloud that you can have in nature or around us? How big can we see clouds which are large, but we also see clouds that are very small. What's the smallest cloud that you can think of? Well, the smallest cloud we know of are those which form in the so-called Saturn rocket assembly facility in the US, where clouds formed. There's a single room which was so tall, so high, the ceiling was so high that there were clouds right on top, small clouds formed. But these clouds cannot be bigger than about a meter at best. Technically and theoretically, it will be of the order of 25 centimeters. That's the coherence length in viscous matter, viscous atmosphere. But about a meter or so is the smallest cloud that you can think of. What's the largest cloud you can think of? I don't know. Quite want to get to that. The largest cloud you can think of, we have observed, the huge cloud in the Indian Ocean, over the Indian Ocean, which is 3,000 kilometers across. Just enormous. After that, beyond that, what happens is the curvature of the Earth starts playing a role, and you don't have a coherent cloud once. Okay. The smallest one is of the order of a meter. The largest one about 3,000 kilometers. That's 6 orders of magnitude, or more, 8 orders of magnitude, or whatever. Not very good at arithmetic, as you can see. We'll come back to clouds. What about Brownian motion? That's something based on power laws and scaling altogether. So if you took a random curve of this kind, it's not representative of Brownian motion, and ask in a random flight of this kind for a certain amount of time, how far can you go from the origin? If I walk purposefully at a constant velocity in a given direction, the time I travel is proportional to the distance I travel is proportional to the time taken. But if I walk at random, like a drunkard's walk, it's not very hard to show, and we'll see that immediately, that we to approximated this path by constant segments, constant length segments, for instance. I ask what's the mean value of the end-to-end vector, mean square value of the end-to-end vector. And that turns out to be just proportional to the number of segments here. And that's a very simple argument, because if you look at the top figure, you see two vectors pointing at an arbitrary direction from each other, with average value which is multiplied by which is the dot product, which is equal to the product of the two magnitudes multiplied by the cosine of the angle between them. But for every configuration like that, there's a configuration in which the second vector points in the opposite direction. And since cos pi minus theta is minus cos theta, the cross terms cancel out completely. Therefore, only the diagonal terms exist, and it says that the mean square distance is proportional to the number of segments n directly to the power 1, or the root mean square distance is proportional to the square root of n. If you take n, the number of segments should be the time for which you walk, then it says that the distance you travel is proportional, root mean square distance is proportional to the square root of the time. The most important square root in the universe, because this square root appears everywhere. This diffusive behavior appears everywhere. Whether it's neutrons in a reactor or whether it's hydrogen condensing into a galaxy, it's the same physics that goes on. So once again, there's a universality here. Now you say, no, this path cannot intersect itself. Like put a long chain polymer in a solution and the path cannot intersect itself because the ligands, when they come close to each other, will repel. So it's a non-self-intersecting walk. And now what happens? Well, one can ask whether the root mean square distance is just twice or thrice what it would have been in the absence of this constraint. Okay. Or does the power itself change? And it turns out the power itself changes. It's not very hard to show. It's very simple. I'm not going to do it here. It turns out that the root mean square distance in this case is proportional not to n to the power half, but n to a higher power, which depends on the dimensionality of the certain system you're talking about. It's 3 over d plus 2, where t is equal to 3 in the normal case, so it's proportional to d into the power 3/5 rather than into the power half. Now, so why does this make a difference? Well, when these polymer people separate out long molecular weight, high molecular weights polymer, chain polymers by centrifuging. You need to know what the dependence on the molecular weight of this rate of centrifuging is. Because these polymers sit in coils, and we need to know what the moment of inertia is in such a coil. And that will crucially determine what the centrifuging efficiency is. And if you have a mix, then if you have a million as molecular weight, for instance, it's clear that a million, square root of a million and a million to the power 3/5 are very different from each other. And that's how polymers are separated by centrifuging, the long chain polymers here. Follows directly from the self-avoiding law. It's got a fancy name. It's called the Flory exponent, which I won't get into here. And so on. And it depends on the dimensionality. And there's a simple argument, which is similar to the argument you give for why the Van der Waals equation has P plus A over B squared, why 1 over B squared and not 1 over B cubed or anything like that. Same argument, it's called main field theory of critical phenomena, explains why this Flory exponent appears here. And today we know how to use the renormalization group to correct the Flory exponent to any arbitrary desired accuracy here. Again, starting with very simple ideas, but going to very profound consequences. It depends on the dimensionality. There are unsolved problems here. I won't get into that here now. Then Levy flight paths, similarly the same thing. So you have diffusion now in a different way. You notice in bacterial solutions, bacteria ingest nutrient solution from a certain region, then they shoot a long distance and go and again do the same thing. And you've seen cows grazing, they do the same thing. Cows graze in a certain area, and after a while they walk a distance, a considerable distance without grazing, go to a new spot and start grazing there. And what they're doing is optimizing the rate at which they take in the nutrients here once again. That has to do with what is called Levy walks here, and there are scaling relations here. And what is interesting is the curdling of milk and the formation of galaxies is exactly the same Levy-Flight kind of physics that we see in both phenomena here. You all know, have heard of this fact that Jupiter is a giant red spot, a huge convection going on. You can see the same physics when you put cream in a cup of coffee and stir it. It's exactly the same physics that goes on. And the same thing goes on at the galaxy level as well. So again, the essential unity of these phenomena and the powerfulness of the general principles with which you understand these things. Well, the scaling in meteorology, once again, if you look at a cloud from below, the cloud has edges, but the edges are wispy and kind of jagged. It's not regular at all. They're fractals, in fact, at that stage. So if I now say the following, I find the perimeter of a cloud by the following trick. Take a satellite with an infrared sensor, put a grid on the photograph. And if in a particular pixel, the amount of water vapor which is sensed by infrared detection exceeds the threshold, I say it's a cloud. If it's below the threshold, I say it's not a cloud here. That way I can attribute a perimeter to the cloud and can ask what is the area versus perimeter law. We took a regular curve on a plane, a smooth curve, and apart from factors of pi and 2 pi and so on and constants, the area, the square root of the area is proportional to the perimeter. But for clouds, it turns out that the perimeter is proportional to the area, not to the power half, but nearly 2/3 here. Once again, it happens because of turbulent diffusion, and there's a theory for it, and that's been proposed by theory. And once again, here's where this in this experiment, that this observation that this Indian Ocean 3,000 kilometer cloud was detected and used, etc. Today, that's advanced to a great extent. There are other phenomena like cloudbursts, thunder showers, etc. Sudden phenomena, which again obey these power laws. And I already mentioned that natural disasters need to obey these power laws or scaling relations. What is it not telling us? It tells us that these phenomena have no natural scale. They're beyond all natural scales. That's the reason for it happening. I'm not going to go into this. This is about Brownian motion. What about good old electromagnetism? Well, we have Maxwell's equations, and in the absence of sources, very far away from the sources, the charge density and the current density, there's the wave equation. Okay. The wave equation involves a del squared operator, D'Alembert operator, which is homogeneous, which is invariant under the scale, the change of length scale and time scale, because both are partial derivatives of the second order in the wave equation without any source terms here. Therefore, the immediate consequence of it is that you have photons or electromagnetic waves of all frequencies and all wavelengths possible. And there's no dispersion in free space. So that's what scaling is telling us in this problem, electromagnetism. And if you put a mass there for the photon or any other object, it's called the Klein-Gordon equation. Immediately the scaling breaks down and you no longer have this possibility. I mentioned there's something about the speed of light, which you can, about the mass of a photon, for instance, the upper bound on the mass of a photon. There's a tabletop experiment to find the upper bound on the mass of a photon. It has to do, finally, when you reduce it to its bare essentials, it has to do the formula that the frequency of a tank circuit in oscillations without a resistive element is 1 over square root of LC. That law gets modified if the photon has a mass. And since frequency is the most accurate quantity we can measure, the most accurate frequency, physical quantity we can measure, it gives you a very nice way of finding out that limit on the photon's mass. By the way, the most accurate clock that we know of is not the atomic clock or anything like that. It's the rate at which pulsars slow down. So the pulsar clock, the glitches in the pulsar slow down the pulsar. That clock is correct to 1 power 10 to the 19 or something like that. Those clocks. Yeah. So nature is already ahead of us in that respect. Well, I'm not going to talk about conformal invariance of gravitational. Let me conclude. I think I've come very nearly to the end of my talk. These general principles are worth emphasizing right from the beginning. And it's worth looking at all, going back and looking at all our textbooks and covering all those elementary examples and seeing what they look like in modern, what they look like with these modern principles, how they illustrate it. I think that would be a much more effective way of inculcating what the subject is all about. It's a wide pasture, and as we all know, it's such a wide pasture that there's no boundaries in that sense. Subjects should be arbitrated. An example should be chosen from as many disciplines as possible. Let's say back very much more. I'd like to end saying that I think it is important to tell the younger generation that matter is not over. Science in its modern form has had only 400 years, whereas philosophy has had 4,000 years. So it gives science a chance here. It's a joke, but I have repeated too many times. It has to do with American comedian Danny Kaye from the last century, whose father emigrated to the US from Poland. Danny Kaye used to tell the story, and when his father was asked why he emigrated, he said his father emigrated because in Poland they told him that the streets in America were paved with gold. But when he reached America, he found out three things in short order. First, the streets were not paved with gold. Second, the streets were not paved at all. And third, they were waiting for him to do the paving. So we're waiting for the younger generation to do the paving. So we know the answer. Thank you.
Before we share the session, we have a small talk from a second
Oh, history. A short history of everything.
Thanks.
Thanks.
Questions? Before going to the questions, I would like to remind again, please make my member of the site forum. Place the QR code, the table, just scan it and fill up the form. You will become the member of the WhatsApp and other groups, social media groups, by scanning the QR code, so that you will get the communication from us. It's going to be the WhatsApp group. Please do that. So let's start the questions.
Do we have any comment on why most of the exponents are of the order of unity?
Answer. Look at the whole Landau theory of these solutions. It starts with the order parameter squared, so that the equation of motion will be linear in the order parameter, etc. In improved interactions, it includes higher powers of magnetization, M, for example, M cubed, M4, etc. Those are the first terms that you start writing down. When you include fluctuations, you start writing down gradient terms, and the simplest scalar gradient term is del m dot del m, del square, del dot m, del m dot del dot del m, gradient squared. So this is the natural way in which you develop fluctuations about the critical value. And that will lead to simple exponents with the small powers, because the powers of m that you're talking about are low. So it's like asking, why doesn't the Lagrangian of a free particle start with the 18th power of the velocity or something like that? Starts with mv squared or something like that. So that's one reason why this happens. A deeper question is, when you do dimensional analysis, you can multiply the answer by any function, any numerical value, which could be a million or 10 million or something like that. Then the whole analysis goes out. And the answer doesn't seem to be very precise. It seems to be imprecise, but it goes like this. It says that if you assume dependence on the right parameters, then the constants of proportionality are bound to be close to unity. If they were like 10 to the 40, then you have an unnatural situation. So there's a naturalness of these small numbers seems to be the hallmark of having chosen the right variables, etc. So the best I can offer is that. Of course, you know that in many two-dimensional problems at critical points, the system is also conformal invariant, which I didn't have time to talk about here. The moment you have conformal invariance, you can use conformal field theory to find the exponents, and they turn out to be rational numbers in two dimensions. This two is a very special dimensionality for technical reasons. So they expect the critical exponents to be rational numbers, but of course, it could be 355 over 787 or something like that. It doesn't happen, except when correction things. But at the mean field level and the first approximation level, it's small numbers that you end up with, not necessarily rational. It's the best I can offer.
Thank you.
Uh, Thank you for such a nice talk, Professor. So, I have a very simple question. So, you sort of asked to make high school students think in a much deeper sense, in a unified sense. So, would that suggest that we remove some topics that we already have in high school, or like, would we have time to teach them in this manner? Like, what is your suggestion?
I think the curriculum should be reduced by 50%. Because some years ago, we had a small meeting in SAP, framing a school curriculum, a unified curriculum from 6th standard to 12th standard in the sciences, a seamless curriculum, including mathematics. A big report was written. We all signed this report, 300 pages long. It presented to NCERT and it got buried forever. And our statement was that the textbook should not be written by experts. They should be written by teachers, very experienced school teachers who are also child psychologists. They know what the kids can understand, what they can't. So certainly the total amount of material should be. In connection with that committee, we asked for the total textbook content of what the sciences were: physics, chemistry, maths, and biology in standard 11 and 12. We got those books in the conference room where we were working on at the table. And when the books came in and piled up, it reached the table height from the floor. Literally. It's absurd to expect anybody to know that. But then it goes the other way also. It's deeply ingrained in our culture. Many years ago, I was in a college board of studies, one of the colleges, and they had in the modern physics course, they had the Bohr model of the atom. Then they had the hydrogen atom, the Schrodinger equation for the hydrogen atom. And in between, they had the Bohr-Sommerfeld elliptical orbit model for the atom, hydrogen atom, included L dot S coupling or whatever. So I said, why do you need this intermediate step? The Bohr model still is useful because in semi-classical physics, it's a starting point, still useful. Although we know orbits don't exist for electrons and so on. And the Schrodinger equation, of course, gives us the truth, quote unquote, as far as we know. So why do you need this in between? Bohr Sommerfeld model. The answer given to me was a very neat 20-mark question. So I tried telling them that that's not the reason why you should hold something like the syllabus which is outdated. It's like saying I'm still going to talk about the caloric theory of heat or the phlogiston theory of heat or Plato's tentacular theory of light and so on. These are gone by the wayside, the waste, historical waste. So you should get rid of it. But I couldn't convince them. So I thought I'd give a little bit of sarcasm. I said, if you're going to change this, there's the Bohr model on the one hand, and there's a Schrodinger equation on the other hand, what we call the truth, the first approximation, and then the actual fact. In between, don't insert anything. If you're going to insert it, then you must do it also of planetary orbits in classical mechanics. Circular orbits on the one hand, elliptical orbits, the correct Kepler's laws on the other hand. In between, you have Ptolemy's 37 epicycles fitted to the orbit of Mars to greater accuracy than even modern physics can predict, because it's just fitting numbers. So you should include that too. Well, a certain number of people, fortunately, the majority laughed. But there was one gentleman who asked me, he said, in which book is that given? We'll include it. Or redemption is not near. So I think it should be reduced, the total amount of content. It's just material content. We had recent occasion, I had recent occasion to look through the state board textbooks, 10th standard, 11th and 12th for physics. There's a lot of material there which is just factual information, which is not necessary at all. Not necessary at all. In the treatment of Doppler shift, for example, they have the source moving, the observer moving, the source moving towards the observer, away from the observer moving towards the source, away from the source, both moving toward each other. Eight possibilities. And there were students on memorizing different formulas for them. Now, I don't think you can write involving the V and the C, depending on what the velocities were and so on. I don't think it's possible to memorize these facts without, blind memorization can be accurate. Make a small mistake. At no stage was there a figure given on what it looks like and what is really happening, why the frequency changes, why the wavelength changes, etc. At no stages is given. Just these eight answers. 8-mark question. So we become prisoners of our own, desire to be as comprehensive as possible. Reasoning is left out. And I also asked some teachers, they said, we generally leave out the portion where the textbooks have questions. Problems, yes. Numerical problems, yes, because it's plugging into formulas. But conceptual questions, that's the thing. And I had a young man come and tell me once, somebody's grandson, one of my colleagues, a friend's grandson, he came and told me that they avoided reading a certain book which the teacher had recommended because it has too many concepts. Okay. So it's avoided like anything. So I think, having said that, I think that the reason our education system hasn't collapsed so far is because our school and college teachers still have a sufficient number of very dedicated people among them who fight against all sorts of odds to keep the system going. This is very important. It brings me to political questions like research institutes versus academic institutions and so on. So I don't want to get into that. Except that once I had an occasion where a very senior person who now no more told me bluntly at a meeting that all that you educationists and people in educational institutes are doing is futile, because no matter what you do, the cream will rise to the top and gravitate towards us automatically. That really annoyed me. So I said, well, when you turn a complex system, complex fluid, it's not always the cream that rises to the top. And in our mythology, this has been proved with our mixed results. What can one say? So I think there are faults on both sides, but there has to be a coming together of people. So there are parts of the country where there are more dedicated teachers than other parts of the country, and you see that in the results of these exams. Of course, the results are horribly vitiated by the fact that there is a certain coaching system that has come into play, and it's beaten the system to some extent. It's definitely beaten the system, etc. But in the longer time scale, these are all passing phenomena, I think. But it's very important to keep our young people's attention alive. And every time we think about this, we have 1,400 million people. And I'm sorry to interject this political note in this, but this 1,400 people If you take all the people we know, all the scientists we know, all the institutions we know, and all the we live in urban areas, all the people we know, etc., all the technical people, etc., are drawn from a pool of maybe 300 million people who've had the opportunity. That's over 1 billion people who are not even in the loop. We had no chance to start with. In fact, a very simple calculation which you can do is if you take Ramanujan, born in 1887 or something like that, if you take the population of Greater India at that time, which included India, Bangladesh, Pakistan, Ceylon, Burma, etc., parts of Afghanistan, etc., population was around 350 million or so, approximately. And if you say that out of 300 million people, there is one Ramanujan appearing every century, on the average, and statistically speaking, then since independence, we should have had 6 Ramanujans. I don't see them anywhere. It's certainly not at that caliber at all. But the law of large numbers can't lie. We must have had them. But the answer is very simple. They belong to the 90% which is left out of the loop. There were 6 of them, but 3 of them were girls. One of them died in infanticide. One of them didn't get medical treatment after grade 2, and the third one didn't go to school at all. And among the boys, one of them became an auto mechanic. The other 2 dropped out of school and became goat herds. They had no chance. That's what we should be fixing. This is my personal view. That's what we should be fixing. We should make primary education mandatory and compulsory for all of them. Give them a chance. Then we'll have our money. We start from a big enough base, we will have a big enough end product here. That's how the Russians used to win all the chess championships, because they taught chess to all the children in their country. We're doing that now slowly in India, thanks to people like Anand and so on, who've been an inspiration. And we are seeing the results. We're right on top. Because you know millions of kids playing chess. So we need to start with the bigger base. And then automatically things will follow. There's no point saying why haven't we got the Nobel Prize and so on. The purpose here is not Nobel Prize. The purpose here is to understand nature. It's not an Olympic Games or anything like that. So this fact, I think we should all be conscious of all the time. The large 4-fold population, which is completely out of the loop, they're in the shadows. It really should bother every one of us. We do our little bit at a time. Like Professor Subramanian Chandrasekhar, one of my heroes, said, he was asked what the secret of his success was, and he said, there's no secret in here. He says, you work a little bit, you do a little bit today, you do a little bit tomorrow, you do a little bit the day after tomorrow. You continue this for about 50 or 60 years, and you have done quite a decent amount of work. What impresses me about that statement is the time scale on which the man thought. It takes time and constant effort. So, pardon?
Thank
Thank you.
That's last question.
Sir, thank you for a great talk, sir. I would like to know whether the quantum world aware of the changes happening in the physical world.
What does that mean, actually? What
like
quantum world?
The subatomic particles and all those,
Yeah.
were aware of the physical and atmospheric changes happening in the materialistic world.
Who should be aware?
I mean, whether it is recorded by the...
That's a very deep question. Whether the microscopic world is recording what's happening in the macroscopic state. The answer is we don't know. We don't know for sure. On the other hand, what we have understood is the following. At every level of magnitude of objects, physical parameters, there are effective laws that work perfectly well. For instance, you say Newton's physics has been superseded by relativity and quantum mechanics. In the regime of applicability of Newton's laws are the final word. They will exist forever. Yeah. For instance, we know that if you want to make a better fuel or a better carburetor for your vehicle, you need to improve the fuel. You're not going to worry about whether the fuel consists of atoms, molecules, and then atoms, and then nuclei, and then subnuclei, and quarks, and you're not going to worry about strings and so on. Your carburetor is not improved by learning string theory. It's improved by learning chemistry, petrochemistry, and so on. So there are organizational laws at every level of nature, and that's what we've discovered over the last 50 years. A collection of identical objects and have properties which the individuals don't have, and it's called emergent behavior. And critical phenomena is just one such manifestation. So at every level, there are effective laws. They may not be the most fundamental or reductionist ones at all. That may never end. But the effective laws are the practical laws that one needs at every stage. Eventually, ultimately, yes, maybe everything is governed by some very primordial laws and so on. We don't know for sure. So, and we certainly don't know some of the mysteries of quantum, many of the mysteries of quantum mechanics. Not the original wave particle duality that we certainly have, macro semantics and so on, but things like entanglement and Hooke action at a distance and so on. We don't really understand. It's entirely possible that we will never understand because our brains are hardwired in a particular way, but I somehow doubt that. I think we will understand it at a deeper level at some stage. And then we will wonder why we didn't understand it earlier. And it's hopeful. But the language may be very different from what we know.
Attraction repulsion of the cosmic bodies, not balancing in the cosmic cosmology, sir.
What does that mean? Yes.
Attraction repulsion of the cosmic bodies.
Yeah.
You said about the Big Bang theory, without any collision to take place, any attraction repulsion of the cosmic masses are not balancing.
Well, you're asking why did the Big Bang occur? I don't know. We're not sure of the nature of the singularity. We're not sure if there's actually a singularity. If we look at quantum effects correctly and so on, we don't know. In short, we don't know how to combine gravity with quantum mechanics in a consistent way. So that's still an unanswered question. We don't know what set it off. We don't know what happens when things fall into a black hole, for instance. There are lots of works on this and the information paradox and so on. We're not sure. The short answer is we're not sure. Partly because we've not understood how to combine gravitation with quantum mechanics in a consistent manner. We don't have an effective theory for that. A lot of work has been done under restricted conditions and so on. We've got some understanding, but not at a fundamental level. You may even be asking the wrong question.
So any other questions? Yeah. Thank you, Professor. In my mind, that number of scaling parameters are keep on increasing day by day when you explore more towards nature. So this is not the end. Maybe after some time, this may be false also, whatever they have found out, because they are knowing the nature, not inventing.
I won't say false. I would say that maybe restricted to a certain range of parameters. Because we're testing whatever our theories are, we're testing against the experiment. That's the final test ultimately. We're testing it and moving on only if it's testable, only if it is verified and so on. If we say under such conditions, this is happening and the laws for this are such and so on. Where those laws come from, we have to understand the deeper theory. They may be the overarching theory which subsumes whatever is said here. But it's not going to say this is wrong. That's
One of my experience, sir, during my school studies, I have studied radio waves will travel through ether. It is in the space. After that, it is disproved. We all know it doesn't require any carrier passing the electromagnetic waves. Even in vacuum, it is passed. First, I have studied in my book. I remember still, it is disproved. Similarly, is there anything going on in the after that? I don't
think you should say that. It's true that this luminiferous ether, which was postulated before relativity, has been debunked. It's not there. There's no such thing. On the other hand, it's coming back to haunt us in the form of what's called dark energy.
Yeah.
Maybe another name for the ether. The original ether was considered as a jelly with certain vibration properties and so on. That's gone, of course. But we still don't know. It's a sobering thought that 75% of matter is dark matter. We don't know what it is. dark energy, we don't know what it is.
Yeah.
Another 20% is dark matter,
Exactly.
we don't know what it is. And 5%, we think we understand. We think.
Thank you, sir. Thank you, Professor.
Like John Wheeler said, as our knowledge grows, as knowledge is an island, the periphery of ignorance also grows. The new questions, more questions arise than have been answered. Which is good, otherwise we'd be out of a job.
Can I? So how about the Boltzmann constant? Is that at the same level as G, H, and C, or is there a different
Deep
character?
question. No, I would say no. It's not. Boltzmann's constant is not a truly fundamental constant. It arose because we introduced a quantity called temperature, which is historically unnecessary, which is historical, in fact, in nature, but which is unnecessary. So K is the conversion factor between temperature and energy.
So you can formulate thermodynamics without introducing temperature at all.
We shouldn't have called it temperature. We should have just said the rate of change of the log of the number of accessible states with respect to energy
Right.
is the inverse temperature. We should have said that. We shouldn't have called it temperature to start with. We should have called it the derivative of the energy or the number of accessible microstates. And we should have used 1 over T instead of T. But that's what appears naturally.
So then it can be thought of as our something to do with our choice of units then? I mean, the fact that we use Kelvin.
Yeah, it's not on the same level as entropy is not quantized the way action is or angular momentum is not quantized. One would be tempted to think it's in a quantum of entropy, but that's not true.
But it is a log of an integer, right?
Log of a number, yeah.
So in that sense, it is discrete, log of some discrete.
Well, but it can take on arbitrary values.
But it should be log of some integer, right?
Yeah, if you're willing to call 10 to the 24.
Yeah. It is still a number. It's a large number, but yeah.
Yeah, that's true. It's certainly true in that sense. It's like saying, is the angular momentum of a fan quantized or not?
True.
If it's 1 joule second in angular momentum, then the quantum number is of the order of 10 to the 24. So the question is, it's a moot point whether you want to call it a continuous variable or discrete variable.
Yeah.
Yeah, I agree. The non-zero nature of Boltzmann's constant also tells us that nature is granular in nature. If you didn't have granularity, if you didn't have a discrete mass for the electron, if you didn't have a discrete charge for the electron, if you had zero Planck's masses went down to zero continuously, charges went down to zero continuously, Planck's constant, Maxwell's Boltzmann's constant vanished and so on, then hydrodynamics would suffice to explain the entire universe. Everything would be in terms of partial differential equations. Matter is resolved right there, but that's not true. Yeah, the granularity of natural constants is what is responsible for what is going on around us. And that's certainly true.
And Avogadro number is also our choice of units, I guess that brings it.
Yeah. Eventually, yes.
Okay.
We've called the inverse temperature the temperature, then this puzzle about what is absolute zero would not have arisen. Because it would be infinite, and you can't attain infinity in a finite number of steps. That would have been the end of the matter. But because we said minus 73.15 Kelvin Celsius or whatever it is, there's this business of is there a block point, why can't you go below that? And then there's this thing about negative temperatures and so on. But if it had been infinity, that would have been fine. We can't reach infinity just as you can't reach the speed of light.
Hi. What about like different constants that are dimensionless that appear in other fields of physics, but they have no obvious relation to HC or G? For example, the Feigenbaum's ratio that appear in period doubling bifurcations. There's probably not a very clear answer relation to HC or G, but they still appear very fundamentally. So what about them?
You're really asking, is there pie in the sky? Or is it in our minds? Does nature actually exhibit mathematical constants, or is it in our minds, in our construct of our mind? That answer would take, I wish I knew the answer to that. And so, don't know. I think it's a little bit of both. Because mathematics is inherent in nature and not in. You can't say where that ends and where the construction in our mind starts, because our mind is also part of nature. That simplistic sense, everything is inherent in nature. So the mystery to me is, why is it that we're able to understand and ask these questions? They are not needed for survival. Some kind of bonus that we've been given. We can even frame these questions and ask them. So, but whether natural constants like pi and e and so on, they manifest themselves in nature in many ways, in physical laws and things like that. But they're asking a deeper question. Are they really fundamental constants in that sense? And no, I think that's not true. But certain constructs seem to be universal, like prime numbers. They're the same in every base. So those are truths which we know, but whether we call them natural truths or whether we call them constructs or consistent conclusions from our mathematics, I don't know. Would be the question.
Okay, we'll have the last question. So almost 1.5 hours over.
Sir, if I look at the distribution of time which it takes between two collisions in a gas, that follows an exponential minus t over tau distribution. This looks very similar to the Boltzmann factor of energy over KBT exponential. There be something between the two.
You know that you can do statistical mechanics, you can write e to the beta h minus beta h as e to the IHT with an imaginary time. So the mapping between statistical mechanics and quantum mechanics involves imaginary, going to imaginary time, purely mathematical construct. So that's the thing that does exist. That's it. But the e to the minus t over tau for collisions appears because it's the first term in the Boltzmann probability distribution. The fact that zero collisions occur up to a time t is proportional to e to the minus t over tau. It's exactly the first n equal to 0 term of the Poisson expansion. So it has more to do with the fact that the collisions are uncorrelated with each other. In fact, that's an interesting point. If you take the time axis and put a cross every time a collision occurs between two particles, put a cross here, the crosses are completely uncorrelated under the normal circumstances. Then you can ask the following question. If I start my clock at some t equal to 0 by putting a bar on this, or putting a marker on this time axis, what is the mean time it takes to get to the first collision? So the mean time between collisions is tau, between two crosses. Now you put a bar here and say what's the time between the bar and this, that's called the forward recurrence time. Similarly, what's the time since the previous collision, that's the backward recurrence time. That also turns out to be tau. That's because the collisions are uncorrelated and probability is a more weird subject than one can imagine at first sight. So it comes entirely from the fact that the collisions are uncorrelated with each other. A little bit like the buses running on the city streets. The arrival time of buses is completely random. And buses will bunch up and there's a bunching effect that goes on, etc. They're completely uncorrelated as far as one can tell. Almost a Poisson distribution.
All right. Can we conclude? And there is no question, then let me, vote of thanks. And first, let me thank Dr. Balakrishnan. We had been following him for 2 years. Somehow it has not happened. At last, we are fortunate to have his lecture today.